of Ingo Sick. Ingo, with Bernard Frost, received the 1987 Bonner Prize for elegant studies of nuclei using high-energy electron scattering, and in particular measurements of nuclear charge and current densities. So this is lead 208, the elastic electron scattering cross-section was measured over 12 decades. And from that, Ingo directly determined the elastic charge density. So the black dash curve is the model-independent experimental charge density for lead 208. And these elastic charge densities quite literally are our picture of the atomic nucleus, and they of course have had tremendous influence. So this is a simple relativistic mean field model for lead 208. The dashed red curve is the point proton density if you fold the single nucleon form factor and add smaller meson exchange currents. You get the solid red curve, so that's the model charge density. And this model is in reasonable agreement with Ingo Sick's experimental charge density for lead. So now we want to go on and look at the neutrons. So the black dash is the point neutron density. If you fold the neutrons with the weak form factor of a single neutron and add a small contribution associated with the weak charge of the protons, you get the solid black curve. So that's the weak charge density in lead. So the black curve is the weak charge density, and the red curve is the electromagnetic charge density. And with parity violating electron scattering, we can probe this, we can measure this weak charge density. And in particular, the goal of the CREX experiment, measure at a single low Q squared and determine how much the weak charge density sticks out compared to the charge density. And this is measuring the thickness of the neutron skin. So we use parity violation to isolate the neutrons. The weak charge of a proton is small. The weak charge of a neutron is big, so the weak interactions at low momentum transfers provide this very clean probe of the neutrons. What's actually measured is the parity violating asymmetry. So it's the cross-section difference for left-handed and right-handed helicity electrons. This involves the interference of a weak amplitude of order G Fermi, an electromagnetic amplitude of order alpha. Q weak is the total weak charge of lead. And FW is what the experiment measures. That's the weak form factor. So FW is the Fourier transform of the weak charge density, which is essentially the neutron density. And by measuring the parity violating asymmetry, one can, in principle, model independently map out the distribution of weak charge in a nucleus. And so this electroweak reaction is free from most strong interaction uncertainties. There's motivation for these parity violating measurements in several different areas of physics. And I want to briefly mention motivation in atomic parity, coherent neutrino nucleus scattering, equation of state and neutron star structure in astrophysics, and then finally, of course, nuclear structure. So to start with atomic parity, in atomic parity non-conservation, this depends on the overlap of the atomic electrons with the neutrons in a nucleus, and so it depends on where the neutrons are. The existing Colorado cesium experiment measures the weak charge of cesium to about 0.3%. This experiment is probably not limited by uncertainty in the neutron radius, but a future, somewhat more accurate parity experiment would need to know the neutron radius to 1%. And so measurements of the neutron radius with parity violating electron scattering in lead and calcium can constrain the nuclear theory to calculate neutron radii for a variety of other nuclei of interest in atomic parity. And in particular, just to mention one nucleus, francium is a very interesting atomic parity candidate. It has the same relatively simple atomic structure as cesium, but the higher Z of the nucleus greatly increases the overlap of the electrons with the nucleus. And so the parity non-conservation in francium is 18 times larger than in cesium. So there's great interest in measuring parity non-conservation in radioactive francium atoms. Another area of motivating the electron parity non-conservation, parity violating experiments is coherent neutrino scattering. So neutrino nucleus elastic scattering depends on the square of the weak charge of a nucleus, so the cross section is very big, and it depends on the square of the weak form factor. So the parity violation measures the weak form factor itself. The neutrino scattering measures the square of the weak form factor. There's great interest in coherent neutrino scattering for several different reasons. One example is coherent scattering provides the so-called neutrino floor, that there's an irreducible background from neutrino nucleus coherent scattering in dark matter experiments, and it may be difficult to push the sensitivity of these dark matter experiments below the neutrino floor. Parity violating electron scattering can constrain the weak form factor better than near future neutrino scattering experiments. So for example, the existing coherent experiment at the spallation neutron source in Oak Ridge has probed the average neutron radius for cesium plus iodine to about 15%. A future high statistics neutrino scattering experiment could probe the neutron radius of a variety of different nuclei to something like 5%, or perhaps a little better. In contrast, CREX has measured the weak radius of lead with parity violating electron scattering to 1.3%, and the CREX experiment I'll talk about today has probed the weak radius of calcium-48 with a sensitivity of 0.7%. So constraining the weak form factor with parity violating electron scattering allows coherent neutrino scattering to be used to probe non-standard neutrino interactions. So parity violating electron scattering and coherent neutrino scattering are complementary. Okay, and one third area of motivation is neutron-rich matter in astrophysics. If you compress almost anything enough, electrons react with protons to make neutron-rich matter. Material is at the heart of many fundamental questions in nuclear physics and astrophysics. What are the high density phases of QCD? Where did the chemical elements come from? What's the structure of many compact and energetic objects in the heavens? And what determines their electromagnetic, neutrino, and gravitational wave radiations? A heavy nucleus such as lead-208 is expected to have a neutron-rich skin. So if we can very cleanly probe the neutron-rich skin with parity violating electron scattering, we can directly study neutron-rich matter in the laboratory, and this has implications for astrophysics and the structure of neutron stars. Great, so let me start with the PREX experiment. This experiment involves almost all of Jefferson Laboratory in Virginia. An intense polarized electron source, many beam monitors to control systematic errors, the electron accelerator itself, and isotopically enriched lead-208 target, and then the scattered electrons are collected in two large high-resolution spectrometers. So the polarized electron sources over here, electrons are accelerated down and back to about 1 GeV. They go into Hall A, where the experiment, where the scattering takes place. So the measured parity violating asymmetry is about 550 parts per billion. So this is 1 GeV electrons scattering at about 5 degrees from lead-208. The combined statistical and systematic error of the experiment is this shaded green band. So if we compare that parity violating asymmetry to a variety of model weak charge densities, so a series of relativistic and non-relativistic density functionals. So you take a weak charge density, accurately calculate the parity violating asymmetry, including Coulomb distortions, carefully average that asymmetry over the angular acceptance of the experiment, and that leads to these points here. And then if you compare the parity violating asymmetry to the measured one, one can use this correlation to deduce the weak radius of lead-208. So this is the RMS radius of the weak charge distribution in lead, and the combined PREX1 and PREX2 result is 5.8 Fermis. This error is, again, the experimental error. It's a combined statistical plus systematic. This 5.8 Fermis for the weak radius can be directly compared to the experimental charge radius, which is 5.50 Fermis. And so we have direct experimental confirmation that the weak charges i.e. the neutrons, stick out further than the electromagnetic charges, i.e. the protons. And indeed, our result for the neutron skin in lead is 0.28 plus or minus 0.071 ferns. So those are the PREX 2 results for lead 208. So the pressure of neutron-rich matter pushes neutrons out against surface tension. So a thick skin in lead 208 is correlated with a large pressure for neutron matter. That same pressure holds up a neutron star against gravity. So a measurement of the neutron radius in lead has important implications for the pressure of neutron-rich matter and for the structure of neutron stars. A neutron star is 18 orders of magnitude larger than a lead nucleus, but it's the same neutrons, the same strong interactions, and the same equation of state. Okay, so let me compare laboratory measurements on finite nuclei with astronomical observations of neutron stars. One can measure radii, so PREX is measuring the neutron radius of lead. NICER is measuring the radius of a neutron star. NICER determines the X-ray light curve and infers the neutron star radius by looking at the curvature of space near the neutron star. I'll say a little more about that in a second. So those are radius measurements. One can also make polarizability measurements. If you scatter one nucleus off another at large distances, the Coulomb field can Coulomb excite one of the nuclei, and one can infer the electric dipole polarizability from Coulomb excitation measurements. Likewise, if you scatter one neutron star off another, the neutron star can tidally excite its neighbor, and the gravitational wave detector LIGO use this tidal excitation to measure the gravitational deformability of a neutron star. So that's the terminology in the gravitational wave field. Perhaps in hadron physics, the same quantity is the quadrupole polarizability. So LIGO is measuring the quadrupole polarizability of a neutron star with tidal excitations, and one can measure the electric dipole polarizability of a nucleus in the laboratory with Coulomb excitations. Let me briefly mention systematic errors for all four boxes of this little table. So I will talk some more towards the end of the talk about systematic errors for CREX. NICER has to model these X-ray light curves. So there are systematic errors associated with the NICER measurement, and that probably is a fundamental limit on these kinds of observations of neutron star radii. So if you made a 10 times bigger X-ray telescope, you may not be able to use the improved statistics to a full measure because of these systematic errors. In contrast, the gravitational deformability, the present LIGO measurement is statistic limited. Furthermore, to calculate the gravitational deformability, it only requires the equation of state and general relativity. So it's believed one can measure the quadrupole deformability, the polarizability, or the gravitational deformability of a neutron star with small statistical errors. So the small statistical errors motivates a third generation, a more sensitive gravitational wave detector, such as Cosmic Explorer in the US or the Einstein telescope in Europe. And such an observatory could measure the deformability of a neutron star with small statistical and systematic errors. Great, so just a couple words on the deformability. So if you start in the ground state, excite with the quadrupole tidal field of the other neutron star, so that matrix element goes like the size of a neutron star squared. You square the matrix element, so that's the radius of the neutron star to the fourth power. You divide by an energy denominator. For a gravitational system, the energy denominator scales like 1 over the radius of the star. So together, this combination goes like the radius to the fifth power. So the quadrupole polarizability scales with the radius of a neutron star to the fifth power. And then LIGO, during the merger GW 170817 of two neutron stars, has set an upper limit on this deformability. NICER is an X-ray telescope that's attached to the International Space Station. NICER measures the light curve of a neutron star. So if a neutron star has a hot spot, this hot spot is associated with a magnetic pole. If that hot spot faces you, then you observe it, and that's a maximum in the light curve. If the hot spot is on the far side of the star, then you see part of the hot spot because of the curvature of space. So the depth of the minimum in the light curve, basically the curvature of space fills in the minimum in the light curve. So by measuring the depth of this minimum, NICER infers the curvature of space near a neutron star, and that's depends on the radius of a neutron star. So this is the way NICER infers a neutron star radius. Okay, so let me plot the deformability of a neutron star. So this is what's measured by LIGO. This is the deformability for a 1.4 solar mass neutron star. Here's the radius in kilometers of a 1.4 solar mass neutron star. And then finally up here is the neutron skin in lead. So it's the neutron radius minus the proton radius in Fermi's. So these blue circles are a series of relativistic density functionals. Given a density functional, we can calculate the properties of lead. We also calculate the equation of state, determine the radius and deformability of a neutron star. So one functional implies all three quantities. Now, the present limit from the merger GW 170817 by LIGO is something like that this deformability should be less than about 600. So LIGO favors small values of the deformability. If you compare that to our blue points, this suggests that the radius of a neutron star is less than about 13 kilometers. So LIGO favors neutron star radii 13 kilometers or less. And then here's the nicer result for this particular neutron star. The radius is about 13 plus or minus 1 kilometer. So the nicer result and the LIGO is consistent in this band between 12 and 13 kilometers. And then if we add the PREX2 result, which suggests that the neutron skin in lead is relatively thick, then the PREX result suggests the neutron star radius is 13 kilometers or larger. PREX is consistent with nicer. There's some tension with LIGO. Basically, LIGO is 13 kilometers or less, and PREX is 13 kilometers or more. So there's a little bit of overlap. So there's some tension, but they're not inconsistent. Okay, so I said because of systematics, it's hard to significantly improve nicer. I will talk about CREX, which is a follow-on experiment to PREX. So let me just end this section of my talk talking about a greatly improved deformability measurement. So how could you greatly improve this LIGO observation? So Cosmic Explorer is a proposal for a next generation gravitational wave detector for the 2030s. This detector would have 40-kilometer arms. So it's a laser interferometer. The arms are 10 times longer than the present 4-kilometer arms. For LIGO, Cosmic Explorer would have 10 times the sensitivity of LIGO, and so it would detect neutron star mergers at 1,000 times the rate. And this observatory could accurately determine the deformability of neutron stars. So this is certainly a very exciting future prospect. Great, so that was a little bit of astrophysics. Allow me to talk just a little bit about nuclear structure, and then I want to present the CREX results to finish my talk. So nuclear saturation is a fundamental concept for nuclear physics. This was already suggested in the 1930s with the semi-empirical mass formula. And nuclear saturation typically means there's a minimum in the energy versus density curve for infinite nuclear matter. So the curve saturates, has a minimum at nuclear density. Of course, infinite nuclear matter is a fictitious system, doesn't exist in nature. Nuclear saturation also means that the baryon density in the interior of a heavy nucleus should be approximately constant. Despite nuclear saturation being such a fundamental concept to nuclear physics, the baryon density in the interior of a heavy nucleus has never been directly and cleanly observed. For example, calcium-40 is the largest stable N equals Z nucleus, but this is too small to have a nearly constant interior density. We have charge density for heavier nuclei, but those heavier nuclei are neutron-rich. They have more neutrons than protons. And so the charge density, the proton density alone, doesn't determine the interior baryon density. So PREX2 provides the first clean measurement of the average interior baryon density of a heavy nucleus. And this is fundamental for nuclear saturation. So we want to determine the average interior density of lead-208. And so to determine the average density, our procedure is to fit a simple two-parameter Fermi function to the weak charge density of lead, and then use that Fermi function to determine the average interior density. And so what's crucial is the normalization of a Fermi function that has a surface thickness parameter A and a radius parameter C. So this normalization, the interior weak charge density, depends on the total weak charge of lead that's given by the standard model. The atomic cesium parity experiment has measured the weak charge of cesium to 0.3%. So not only is it given, but is the weak charge given by the standard model, but the atomic parity has confirmed that. And then this is a density. So it goes like the weak charge over the radius actually cubed. So the idea is to use the measured PREX2 value of the weak radius. There's a small correction from the surface thickness. So in principle, one can measure the surface thickness with a separate parity experiment at slightly higher momentum transfer. But until we do that, at the moment, we have to take the surface thickness from theory. So we look at the average surface thickness of a whole variety of density functionals and take this value from theory, use the PREX result for the weak radius of lead. That allows us to infer the interior weak charge density of lead. And so let me show you that picture. So the red curve is INGO 6 experimental charge density for lead. The dashed line is a Fermi function fit to INGO's density. The blue curve here is the Fermi weak charge density that fits the PREX results. So this is the measured interior weak charge density in lead. The error bar here is primarily the error in the weak radius from PREX. There's a small contribution from the uncertainty in the surface thickness. One can combine this weak charge density, which is primarily the neutrons, with the charge density, i.e. the protons, to get the total baryon density. So this is the PREX2 determination of the average interior baryon density in lead-208. So this value is the first clean observation of the interior baryon density of a heavy nucleus, this fundamental concept for nuclear saturation. Okay, one can compare that to calculations of the saturation density of infinite nuclear matter. So let me emphasize this theory calculation is for infinite nuclear matter. And this is clearly for lead 208. The observation, again, nuclear matter is fictitious. Bear with me just a second, excuse me. Great, so the Drischler et al. Is a chiral effective field theory calculation, the energy of nuclear matter, symmetric nuclear matter versus density. The red is an N theory free LO calculation. And this ellipse here is the inferred error ellipse for the saturation density and binding energy of infinite nuclear matter. So that's this black point here. So in the future, it would be great to have ab initio or microscopic chiral effective field theory calculations directly of the interior baryon density in lead. Alternatively, the difference between the interior baryon density in lead and the saturation density of nuclear matter only depends on three quantities, which are all expected to be small. Coulomb corrections slightly decrease the baryon density in lead, while surface tension corrections increase the baryon density in lead. So there's some cancellation between those two. And then lead is a somewhat neutron-rich system, while symmetric nuclear matter is assumed to have equal numbers of neutrons and protons. So the saturation density of nuclear matter probably decreases as one goes away from equal numbers of neutrons and protons. Okay, great. So the last thing I want to talk about is CREX. So this is a measurement on calcium 48. In chiral effective field theory, 2 and 3 nucleon forces are expanded in powers of a momentum transfer over the chiral scale. 3 neutron forces are very important for the neutron skin in both lead and calcium. If you'd like to do an experiment on a stable, neutron-rich, closed shell nucleus, you basically have two choices, lead 208 and calcium 48. So CREX measures the neutron skin in calcium 48, and this smaller system allows a more direct comparison to microscopic chiral effective field theory calculations of the neutron density in the neutron skin directly in calcium 48. And again, these are sensitive to 3 neutron forces. So again, the CREX parity experiment involves many beam monitors and a great deal of work to control systematic errors. The target is isotopically enriched. It's about 92% calcium 48, and the rest is primarily calcium 40. Okay, so I apologize, this is somewhat slightly confusing slide. I wanted to show systematic errors. So bear with me a second. Let me get to the end here. So the measured parity violating asymmetry. So this is 2.2 GeV electrons scattering at about 4.5 degrees from calcium 48. So the measured asymmetry is 2.66 times 10 to the minus 6, or 2,600 parts per billion. And this uncertainty, 4.3%, that uncertainty is mostly statistics and a small contribution from systematic errors. So a great deal of work has gone into controlling the systematic errors. And here's a list of a number of the systematic errors for the experiment. Let me just comment on a couple of these. So acceptance normalization is basically depends on very accurately knowing exactly the scattering angle of the experiment. And the experiment accepts a small range of scattering angles. And so there's a number of auxiliary measurements to determine exactly what those scattering angles are. And they're compared to Monte Carlo simulations to understand this acceptance. And so there's a small uncertainty in this acceptance, and that leads to a systematic error of almost 1%. So this 0.9% is the largest systematic error, but that's still significantly smaller than 4% statistics. One more systematic error actually comes from the first excited state of calcium-48. So this is a 2+ state at about 3.5 MeV of excitation. And the acceptance of the high resolution spectrometers were such that about 0.5% of the rate came from this excited state. So the great bulk of the rate came from elastic scattering. There's a tiny contribution from this inelastic excitations. So we need a robust estimate of the parity violating asymmetry of this excited state. And we've done that. We can make an estimate in a number of different ways. And let me just take an opportunity to thank P.G. Reinhardt, Chevy Rocamaza, and Jorge Pikarevich for providing RPA calculations of this 2+ excited state in calcium to help constrain this systematic error. Okay, so here's the measured parity violating asymmetry. And from that, if you take a model weak charge density, include Coulomb distortions, calculate the parity violating asymmetry, carefully average that asymmetry over the experimental acceptance, and that allows you to basically determine a weak charge density which is consistent with the measured parity violating asymmetry. And then for that weak charge density, you take its Fourier transform, which is the weak form factor. You take the Fourier transform at this average momentum transfer. And so this is the way we deduce the weak form factor of calcium-48. So the Fourier transform, the weak charge density of calcium-48 is 0.13, and this is a 4.5% error. Basically, it's equal to the error in the parity violating asymmetry. Okay, so that's a main result from the CREX experiment. Now, the charge form factor at the same momentum transfer is about 0.153. So this is the Fourier transform of the known charge density. So let me plot the charge form factor minus the weak form factor. And so here's the CREX result, and here's the momentum transfer of the experiment. And we've also shown a series of model curves The model curves correspond to a simple two-parameter Fermi weak charge density. The surface thickness is taken as an average of a whole bunch of density functional models, and then we vary the radius parameter. So this green curve has the weak radius 0.1 Fermis larger than the charge radius. The blue curve is 0.15 Fermis larger. This is 0.2 Fermis larger. And then finally, the black dot dash curve up here has a very thick weak skin where the weak radius is 0.25 Fermis larger. So you can immediately see that the model independent weak form factor from the CREX measurement is consistent with a weak radius being something like 0.14 Fermis larger than the charge radius. So the weak skin in calcium-48 is measured by CREX to be significantly thinner than the skin in lead-208 as observed by PREX. Okay, so that was the charge minus weak form factor at the momentum transfer of CREX. And we can plot on the x-axis here the same quantities for PREX. So here's the PREX result, the relatively thick skin in lead, and then there's the thin skin in calcium-48 from CREX. And the yellow is a combined confidence level for the two measurements. So this is 1 sigma, and then the larger one is the 90% confidence level. And then here we have a series of relativistic mean field models, and PREX alone was getting a thick skin up here, but now with CREX and its thin skin, we're favoring models which are actually somewhat below the 1 sigma error bar for PREX. So CREX has a much thinner skin, and combined CREX and PREX seems to be favoring results a little bit more than 1 sigma below the PREX result. Okay, let me just try and summarize here and look forward to your questions. So from the measured parity violating asymmetry and the acceptance of the detector, we've determined the weak form factor, the Fourier transform of the weak charge density. So here's the CREX result. The only assumptions for this result are that Coulomb distortions and radiative corrections have been included correctly. So there's very little model dependence in this weak form factor. If you want to go beyond that and extract a weak radius, there will be a small model error. So technically, the RMS radius is the derivative of the form factor at 0 momentum transfer. CREX wasn't done at 0 momentum transfer. In fact, it was done at a relatively large momentum transfer here. So one needs to make modest assumptions about the surface thickness of the weak charge density in order to extract a weak radius from this form factor measure. So the weak radius, when it's extracted, we'll have an experimental error. So the experimental error is the statistical plus systematic error in the measured parity violating asymmetry. That error will be about 0.025 Fermis. So that's 0.7% of the weak radius of calcium-48. But then it will also have a model error associated with the assumptions about the surface thickness. We are working on that model error. We estimate it just by looking at the range of surface thicknesses predicted by a large variety of theoretical models. This surface thickness is also constrained by the measured surface thickness of the charge density. So we estimate the model error is going to be something like 0.012 Fermis, so significantly smaller than that error. So stay tuned. We're working on this, and we want to ensure that our procedure for extracting the weak radius is as robust as possible. Okay, and let me just emphasize what we call the weak skin is the weak radius minus the charge radius. And finally, the point neutron radius follows from the weak radius if you also make assumptions about the weak current operator. And so that weak current operator actually includes significant spin orbit currents. And these spin orbit currents give a net contribution to the neutron skin or to the weak skin, which is actually larger than this experimental error. So to extract a point neutron minus proton skin for calcium-48, that necessarily involves at least some assumption about the weak current operator. Okay, great. Let me finally mention, in the future, MREX is a proposed experiment at Mainz. You can call it super PREX. So this experiment measures the neutron radius of lead with the goal of improving on the error bar from PREX2 by more than a factor of 2. So that's something for the future. Let me emphasize the large number of PREX and CREX collaborators. Let me also emphasize Brendan Reed is a graduate student at IU working with me, and he's made important contributions to both CREX and PREX that I've talked about here. So thank you very much for your attention. I'm happy to take your questions.
Thanks so much, Chuck. That was a very interesting and very clear talk. In particular, of course, besides all the nice results, I like your brief Astro introduction. So just in interest of time, at this point here, let me emphasize that there's going to be a second talk, if you like, on the symmetry energy and related topics. So Jim Latimer is going to talk about the nuclear matter symmetry energy from experiment, theory, and observation. And this talk is going to be at the INT, but you can join virtually as well. So let me just post here in the chat box the link, the Zoom link, if you want to join. So this is at 10:30 a.m. Pacific time. Okay, so then let's get started with the Q&A session, and perhaps just to break the ice, if there's ice. So when can we expect the CREX paper on the archive?
Christmas may be optimistic. The collaboration talks about that. So let me say Christmas or early in the new year.
Okay, That would be a nice Christmas gift for the community. Okay, so if you have questions, and I can see lots of them, just raise your hand and go ahead. So let's get started with Pablo. I think you were the first one. Just unmute yourself.
Oh, thank you, Christian. Thank you so much for coming, Chuck. I enjoyed hearing your talk. So my question is very to the point and technical. When you were talking about the symmetrized Fermi function that you were using to make many of the results or discuss many of the results for PREX, you were fixing A, but letting the experiment guide your value of C. And you were fixing A by making this average of all these other modes that you have. Do you think, I'm just curious, do you think if you instead let both parameters be free and maybe have some prior distribution over them and revisit the results, there will be any change on that?
Yeah, so PREX itself is one number. So you can't constrain two things with one number. It would be great to have a second measurement. So if you did a second experiment, and this could be done at the microtron at Mainz, then this measurement is a slightly higher q², and that would allow you then to determine A and C separately directly from experiment.
But you could have like instead of having A fix, I know what you say that you have only two measurement and two quantities, but if you use a distribution of parameters, like in a Bayesian way, for example, that could come from theory, because I'm just, I don't know, worried that you're...
Yeah, so a very simple and very unsophisticated way to do that is I just assumed a central value and some error bar and took this range. So some contribution to this width, and in particular out here, is from the surface thickness.
Okay, thank you.
Thanks, Pablo. And the next one is Siduolin, or Shiduolin. Did I get this right, your pronunciation?
Yeah.
Okay,
Yeah,
close enough.
Yeah.
Sorry. Anyway, so what's your question?
Oh, yeah, sure. So actually my question is that I'm just wondering if the measurement from CREX can also provide a constraint on the infinite nuclear equation of state. If it does, I'm also wondering if that kind of the constraint will give us some different information than the PREX measurement does. Yeah, so that's my question. Hope it is clear.
Yeah, your question is clear. And so calcium is a little bit small. So you won't have a very large region in the interior that's flat. So calcium-48 is mostly surface. If you took a heavier nucleus like tin, it would be very interesting to see how the interior baryon density in tin compares to lead. So nuclear saturation says that they should be essentially equal. And that would be a very interesting thing to experimentally verify.
Of course. So if I understand correctly, Chuck, so which means that, I mean, probably the measurement of the calcium-48 is heavily influenced by the somehow like the finite structure of these nuclei. But of course, we know that this kind of the finite nuclear structure effect, probably it can be somehow cleared or taken out from the calculation with the help of something like maybe the ab initio chiral effective field theory, because we know that some ab initio calculations already agrees with the measurement of the CREX. So probably the finite structure effect can be taken out, and we can still get some information of the infinite nuclear equation of state from the calcium-48. I'm not sure, but probably Chuck how if you can have some comments on these things.
Yeah, so let me say, it would be great to have more microscopic ab initio predictions of the interior baryon density of medium heavy to heavy nuclei. So it would be great to have direct calculations in the finite nucleus of the interior baryon density in a variety of nuclei.
Okay, thanks. That's all my questions. Thank you, Chuck.
Okay, thank you. Bill, you're the next one.
Chuck, can you put up figure 30? It's the one where you show the two constraints.
To constrain.
That's the where you have the, that's that one.
Oh,
Yeah.
there we go. Yes.
So am I correct to interpret that the combined probability of probability of these two combined measurements of occurring is at the and being consistent is at the level of 5%? It's a 2 sigma error. Is that correct? I was actually
So I mean, these points
10%.
here are 90%.
90%. So the probability.
10%. Yes.
Yeah, right. It's 10%. Okay. So that's
But
not very
let me caution. You should put lots more models on this page. And there may be non-relativistic models which are closer.
I see. So so basically it could become more probable then.
Yes, I mean the results are the results. This is what we got, and very interested to see where your models are on this plot.
Yeah. Okay. Well, that's my question.
Okay, thank you, Bill. So the next one, according to my list here, is Beishan Hu. Go ahead, please.
Okay. Thank you for nice talk. My question is about when we extracting the weaker form factor from experiment, I think they also have some model dependent. For example, we need to assume the density profile. So I just curious how it's where the model dependence for extracting the weak form factor.
So in the Born approximation, the parity violating asymmetry is proportional to the weak form factor. We know the charge form factor.
Yeah.
So you measure APV and we can deduce the weak form factor. So the only corrections are Coulomb distortions and radiative corrections. So modulo those, we can directly deduce the weak form factor from the measured parity violating asymmetry. So experimentally, you can measure the weak form factor. To model the weak form factor, you need a density distribution and a current operator.
Okay. Okay, thank you.
Okay, thanks for asking the question. The next one is Bob Beringer.
Hi, Chuck. Thanks for the nice talk. Would it be fair to assume from the CREX, or at least the preliminary CREX results, that they will tend to be in better agreement with NICER and LIGO?
So I would have said PREX already was in reasonable agreement with NICER, but modulo that, the short answer to your question is yes. So CREX is definitely softening the equation of state compared to PREX alone.
Okay, thanks.
Thanks. Next one is Sanjay.
Hi, Chuck. Thanks. That was a beautiful talk. Enjoyed it. If you go back to your slide 30 that Bill was asking about, so that seems like a really powerful way to learn about structures and density functionals that may be missing in current approaches. So clearly, there's some other density functional out there with more sophisticated gradient terms or more sophisticated isospin dependencies that can get closer to the intersection point. Can you speculate on what structures those might be?
Yeah, so that's really interesting. I don't know how you make a thin skin in calcium and a thick skin in lead. Maybe there's some gradient term that can try to do that. Maybe it's something about the F7/2 neutrons, calcium, if you do something to put them in a particular place. That's interesting to explore it. I don't know the answer.
So you expect, I mean, would it be correct to expect that all of this engineering of the density functional will have to happen at the level of either the shell structure or at the gradient terms? And if you're trying to extract from the density functional the properties of uniform matter, right? You know, so the strategy is you have a density functional, it's got a bunch of terms that finite nuclei probe, and the smaller nuclei probe it more effectively, these gradient terms perhaps. And then ultimately for neutron star studies, you want to go to uniform matter, which probably is totally insensitive to the structure of these gradient terms. So I'm trying to get an understanding of if PREX is in fact, you know, because it looks at a much bigger nucleus, is probing infinite matter better than CREX is. You know, how do we make use of that information?
Yeah, so, I mean, if you look at, say, the density dependent of the symmetry energy, L, then clearly you march out along this line as you change L, you increase L. But then how you come off this line by doing something with exactly the structure of calcium-48 and the F7/2 neutrons, or if you can have big gradient terms or something. I don't know the answer.
Okay, thank you.
So Bill, you're still raising your hand. Do you have a question? Okay, if not, then let's move on to WashU, St. Louis. Willem Dikhoff, please.
Hi, Chuck. Great talk as usual. I remind you that Jorge has just published a paper which suggests there is some tension with the dipole polarizability and the skin results with mean field. So I would simply recommend in general to look at models that go beyond the mean field because they have more flexibility and you know, can do more, like describe elastic nucleon scattering and so on. So this is, I think, also a message that can be taken away from these two results.
And I'm delighted to think about the polarizability in more microscopic, more sophisticated models.
Okay, so any further questions? Now's the time. Oh yeah, so Scott Pratt, please go ahead. Scott?
Aha, maybe now they can
Okay,
hear you.
I'm sorry, but we were muted. How does the uncertainty in our knowledge of the isospin dependence of the surface energy translate into our ability to determine the isospin dependence of the equation of state? And if it doesn't do that much, did we actually get from these analyses, do we also get a better ability to determine the isospin dependence of the surface energy?
I think yes is the answer to your second part of the question. So you can have a volume symmetry energy and a surface symmetry energy, or you can have the symmetry energy at normal density and the density dependence of the symmetry energy.
Mm-hmm.
So normally we talk about the neutron skin as determining the density dependence of the symmetry energy, but basically that's determining the ratio of volume to surface symmetry energies, if you wanted to look at it that way. So they're completely equivalent. And
Okay, but so what you're saying is that our knowledge, well, this is basically the same as our saying, our knowledge of what the gradient terms should be, because we can have gradient terms that give you the isospin dependence of the surface energy. So you feel that those aren't, that the uncertainty in those terms in particular are not, say, driving this the difference between your mean field models here and the experimental results?
yeah, so I'm saying it's equivalent. So
Okay.
we talk about measuring the neutron skin and that fixing L, but fixing L and J is equivalent to fixing the volume and surface symmetry energies.
Okay.
So did that answer your question, Scott?
Here.
Oops, wrong. Sorry. Yeah, that's fine. I'm a happy guy.
Okay, great. Okay, then let's move on. Zoom says first Pavel and then Sanjay again.
So mine is just a comment, is that symmetry energy, the density dependence of the symmetry energy affects the diffuseness, and that the whole new issue of neutron skin is the interplay between the diffuseness and density dependence of the symmetry energy. And the mean field models often have just a gradient term for range and or very primitive other range. So that's maybe the next step, is to figure out how to better model finite range effects in theory.
Yeah, so maybe I could respond with just a comment. We measure the weak charge density or the weak radius, and how you want to model that with a particular density functional or some finite range forces in a different interaction. That's your choice.
Right. But you know, from your formulas, you were putting there the surface diffuseness, and that's fragile, even when you put the error.
So I would claim in defense of what I'm doing, we've measured the surface diffuseness for the charge density. And it's hard to be drastically different for the weak charge density.
Okay, I'm not 100%. I'm not as sure as you, but let's stop there. Yeah.
Okay, thanks, Pavel. Sanjay?
Yeah, so I just want to follow up with your suggestion that calcium-48 would provide useful input for chiral EFT. And what's the expectation? How well do you need to know the form factor, the difference between the charge and the weak form factor, to start constraining three-body low energy constants in chiral EFT? And which three-body low energy constant do you think will be most sensitive to this?
So I would say the CREX, the existing CREX measurement is pretty accurate. So I believe it will have some impact. Exactly what and exactly how small the three-body contributions will be to explain the thin skin in calcium-48, I think we'll see. But certainly the accuracy of CREX is much better than the spread in a variety of theoretical models.
Okay, so it's already good enough to be competitive with other ways of constraining 3 nucleon forces, say from neutron-deuteron scattering, or systems like that. I don't understand your claim.
So let me be a little bit careful. If you want to use calcium-48 to fit one of your parameters of the chiral interaction, you can do that, but of course you have to be very careful about all the approximations in your calcium-48 calculation.
Okay.
If you determine the three-body force some other way, CREX will be a very good check that the 3 neutron force contribution in calcium-48 is relatively small. You can make some statement like that.
Okay, thank you.
Okay, it's 20 past the hour. I don't see any further questions, so let's call it a session and thank Chuck again. Thanks again for your nice and great talk. So the last word is on the next nuclear theory seminar, which is going to be in 2 weeks. INT/N3S postdoc Sophia Hahn is going to be talking on probing exotic matter in neutron star cores with G-mode oscillations. So I'm looking forward to this talk as well. So have a great day and see you in 2 weeks. Bye.
Bye. Thank you.
Great. Thanks, everybody.
Thanks, Chuck.
So can I try to answer all these chat questions?
Sure.